Today is the third day that we'll be having this session, and today we'll be looking at CIT341 data structures and algorithm. So today has been somehow tough for me. I had some power issues and I was not really able to prepare any soft copy or slide or presentation. So I'll be using what I have, what I jotted down in my notebook for the class this evening, while I open and we use the course material to support. Then I'll also open up the past questions so that we can get started now. Um, okay. All right. Our first question here is telling us to discuss a data type. So that is going to bring us to the question, what is a data type? All right, so according to what I have written down, a data type refers to a defined kind of data that is a set of possible values and basic operations on those values. So in programming generally, we are talking about data types. These are like the kind of data that we work with and we use for different operations. So, like it is said in the material, it defines a set of values and the operations that we can perform on those values. So, the different data types that we have, it actually helps the translator, compiler, or interpreter, as the case may be, to know how to interpret or compile your package, your software application whenever you are building and you are developing your software program. So that's that about data types. So I think there should be example of data types. Yeah, there's classification of data types. So the domain is a set of value, while the operations, the set of operations that are what we apply on that domain, which is a set of value. Now, when it comes down to the classification, we have simple data types and we have data structures. So the common, which are the simple ones, they are the one known as character numeric, numeric, real, Boolean data types. So that's that about discussing data types. The next question,
Hello.
illustrate an abstract data type. So when we say something is abstract, it has to do with guys, please. I'm very sorry for the break in transmission. When we talk about abstract data, when we talk about abstract, anything abstract has to do with a particular concept. It has to do with oh, it has to do with something that has to do with an idea. It's not something solid that you can probably grab hold of or see and touch like that. But something abstract has to do with the concept of an idea that is like brought to life, probably through an imagination, or in this case, through programming.
Hello guys.
So here we are asked to
Please,
illustrate
there is a mistake.
An abstract
I just checked that the NAC
there are
official
different
sent a wrong email.
types of
So
abstract data
please
types.
use this link. This link is the one you are using
abstract
tonight.
data type
Please
is
use
commonly
this.
referred to as
Please
AD.
use this, please.
And
This
is a
one I
collection of
dropped now.
data
Use
objects
it.
characterized by how the objects are accessed. it is an abstract human concept meaningful outside of computer science. But know that object here is a general abstract concept as well. It can be an element like an integer, a data structure, like a list of lists, or an instance of a class. So example of
Yes, ma'am.
abstract
Please use
data
that one.
types, we have our stack, we have our arrays, our lists, our queues, our stacks, and trees. So those are examples of data structures. So although I don't know, by saying illustrate, I think when something has to do with illustrating, it has to do with a little bit of explanation and probably a diagram. I might be wrong, but down somewhere here there should be uh, the drawing of an abstract data type. Meanwhile, I would probably find a means to just draw that one quickly. Uh, all right. So, so when we talk about illustrating an abstract data type, and like I've explained what abstract mean on its own, I'll just quickly try to draw out a stack, which is like a type, an example of abstract data types. A stack is data types in which objects are arranged based on arranged and placed on the inside the data structure based on their order of how they join the list of items in the stack. And when we are talking about a stack, I know the illustration that comes to mind is when you are setting your plates in a cooler or in a particular place. If you are placing those plates, you place them on top of each other like a stack of plates. And if you are going to remove something from plates, you are going to be removing from the top first. So that's why they call the implementation of a stack data structure as in first out, which means the last data items that enters the stack structure is the first one that leaves the stack data structure. So there are a set of operations that can be applied on the stack data structure. We have your pop, we have your push. So there are various operations for insertion and deletion, as well as searching and traversing the stack data structure. So a stack is going to be something like this. You are going to have a container. You're going to have a container that looks like this, and your container is probably going to be segregated into the list of like based on the data items that you are putting inside. So let's say this one is one, this one is two, this one is three, then on and on like that. This one is four, then this one is probably five. So this is like an illustration or a simple diagram of your stack. So as each of these items are coming inside, it is stacked and placed upon each other. It's on top of what you have on ground, and it's going to be placed on top of it and not probably in the middle or below it. And when they are leaving, it is going to be the last one that leaves out. So that means as it is now, if another data item is going to enter this stack, that is going to be number 6, is going to be directly on top of number 5. And if it's going to leave, let's assume that, okay, this 5 is the last item. If anything is going to leave, the 5 will be the one that will be the one to be, get out of the stack what's it called, data structure first. So this is the implementation of a stack, and this is a simple illustration of a stack. So all right, move on to the next question. Examine the concepts. Hold on. Sorry for the little break in transmission. Examine the concept of objects in object-oriented programming. So when we talk about objects, we are talking about containers and concepts that we use to represent. It's all about the concept that we use to represent a real life object. But the whole software package as a whole is bundled, and packaged. The object on its own is a software bundle that has its state and behavior. When we talk about state, we talk about the properties. When we talk about behavior, we talk about the methods. So and these objects, they are used to life and reward objects that we find and make use of in every day actually comes into play, and the whole abstract thing, it makes sense when we are talking about objects in object-oriented programming. So here, for example, now you can have an abstract of your bicycle, which is a very commonly used example in the material as well. So when you look at your bicycle in real life, it's very, very possible for you to have the replication of that as an object. If you're having your bicycle as an object, the state of those bicycles, which should be the property of those bicycles, can be the gear, then the method or the behavior of a bicycle can be represented as like changing the gear or increasing the speed. This is the behavior of a particular bike. So now, I think that's that about. Okay, now there are different concepts involved in object-oriented programming. We have the four major concepts are inheritance, polymorphism, encapsulation, and abstraction. Now, when we were dealing with CIT341, if I'm not wrong, object-oriented programming on Monday, we actually made mention of all these things. But the abstraction is when we look at the concept of a real-life object and presenting it as an idea and modeling your software object to fit that real-life object. Then encapsulation is some sort of a data and information hiding when you don't want your internal operations of the software to be visible to the outside world. Then we have inheritance. Inheritance is a form. It is some sort. The way in which a particular class inherits some properties and fields and variables from its superclass. So by the concept of inheritance, is actually it encourages reusable code. It also encourages it discourages duplication of codes and encourages reusable code. Then what else have I not talked about? Inheritance, encapsulation. Oh yeah, polymorphism. When we talk about polymorphism, is the ability of an object to have more than one form. So polymorphism is like when you have your object or your method, it's the same name, but the data type that's associated with that particular field or variable is different. Take for example, you can have a variable name, let's say my name. Now my name as a variable, you can decide to make it a string. If you make my name a string, it's going to be different from when you say my name, you make it an integer. Although they might be the same name, which under normal circumstances is supposed to raise an error and flag it down that something is wrong. You cannot use two names for this thing. But they will have different signatures because they are of different data types. So that's where polymorphism comes into play, where a single method, a single object, a single field or property can have multiple forms, can be doing multiple things, and be associated with multiple data types. So that's that about explaining the concept of objects in object-oriented programming. Then discuss an array data structure. An array All right, hopefully the recording will continue with the audio as well. So like I was saying, the binary search tree, it attempts to make a balancing of itself to make sure that the way these items are placed in the tree, it will meet up with O log n, like a logarithmic algorithm analysis. And by so doing, it will be better than a linear search, which is O of n. So which is sort of like a O of n. the more the size of that data item that we are traversing increases, the more it will be difficult to handle the large data sets. So that's that about AVL trees. And say discuss the following: inheritance, encapsulation, and overloading. I've kind of discussed some of these when I was talking about the concept of object-oriented programming, but I'll still go over it. Inheritance is the concept, the principle of object-oriented programming in which a class extends a superclass and inherits and make use of some properties and fields that are made available from the superclass. So that is all inheritance is all about. Now, inheritance rely on a special keyword, most especially in Java programming language. It is called the extend keyword. Let's say you have a superclass called my class, and you have another class called subclass, and your subclass wants to inherit from superclass. So all you have to do is just say your new subclass, that's uh your private class subclass extends the superclass. So by so doing, the properties that are public and made available in your subclass will also be usable and accessible inside inside your subclass. So from the from the subclass, you get to use classes that are inside the super classes. So the extend keywords makes it easy to derive one class from another. That's the principle and the mechanism of inheritance. Encapsulation is a fundamental principle of OOP, of the object-oriented programming. What this one involves, like I said earlier, is some sort of data hiding, some information hiding. So the mechanism with which this thing works, the logic of with which it works is not exposed outside. It is encapsulated inside. When we are discussing CIT341 on Monday, I said encapsulation is I actually explained it with the concept of a capsule. If you look at your red and yellow capsule, you are not really familiar with what is inside the capsule. Well, you know that there's a red and yellow covering that is encapsulating it, that is covering it up. So you don't see the internal operations, you don't see the logic that is actually the constituent of the operations of that your red and yellow capsule. All you see is the red and yellow covering. So in the same way, that's what encapsulation is all about. It involves hiding the internal operations, the logic and everything through the method and the functions of an object. So then overloading. Overloading is a sort of like polymorphism. But the difference between overloading and polymorphism is that you can make use of, how do I put it? A single method, but when you are calling it like different types. Take for example, I made mention of a constructor overloading when we did CIT341. We can have a constructor overloading. We can also have a method overloading. Those two types of loading exist. Let me quickly check it from the book here. I'm not very sure. Overloading. Interesting. Well, in our CIT341. Anyways, let me look it up from CIT383. Okay, we have method overloading, constructor overloading, and basic operators overloading. Then others include overloading your Boolean, that's your true or false, and also the logical operator overloading indexers. So overloading is actually when you have the same method, like it is the same method, the same name, but you are using it multiple times with different arguments. So having it with different argument tends of changes the signature like it does with polymorphism. So, but having it with different arguments means that okay, probably one is with two arguments. Then there's another one of the same name with three arguments, and probably the types of the arguments are also different. So I'm still trying to like cycle through to okay. Yeah, many of the classes you will use or create while developing applications will have more than one method of the same name. This technique is called method overloading. So this is some sort of a way in which you have your method. Your method is your function. So your function is like your f of x. You have your f, your x that goes inside the function, which is like the domain of your function. So your function can actually be different, but the function name is still your f of x, is still your f of x, still the same thing. So that's how that goes for overloading. Please, if at any point in time you have a question, don't hesitate to ask your question and we'll get to it. Illustrate the list data structure. So when we talk about the list data structure, I kind of like to think of the list in form of an array, but even though it is not an array, we have different types of lists. We have a circular, we have linked list, we have double linked list. So the list data structure is a sort of a sequential data structure, like it is one after the other. So when we say something is sequential, it follows a sequence. It follows a predefined sequence. So let's say your sequence is like in steps of 3. You know that your linked list will also be in steps of 3. So the collection of items, which is your data items that are placed inside it, is accessible one after the other as well, like a linear item. List data structure. Yep. So in a list data structure, every element of the list is known as your data item. Then the pointer is what links one data item to the other. So from one data item to the other, like from one sequence of data item to another one, that's your pointer links it up. Then when you have your data item plus your pointer, it makes a node. Then you have a terminator, which is the last pointer in the list. So that's your terminator. Then we have the head, which is the first data item of the list. And you have the tail, which is the remainder or last item of the list. There are some couple of operations that can be performed on your list data structure, and we have your add, your set, your remove, your index of, your isempty, your isFull, your initialize, your destroy. So these operations, I would like to refer to them as verbs. Verbs in the sense that they are action words, and what they said they do is what they actually do. The add operation will add an item to your link to your linked list, to your list data structure. The sets what is the operation tends to update and set the value of a particular item in the list data structure. Then remove, we remove an item from, or a node from the data structure. Then get is we fetch a value from it. Then index of, it gets the index. That's the index location, sort of like an index storage. Is empty. Is like a method that checks if this list data structure is empty. Is full, we check if it is full. Initialize it, we kind of create a new list data structure. While destroy, we kind of like the whole process of garbage collection and clearing up unused variables and methods to free up memory. It will move them out and make sure that it is not on the memory again, to free up memory space. Now, this is telling us to illustrate, and let me try to bring it up so that I can just draw it and see what a list data structure looks like. Okay. All right. As we switch this to landscape so that it is better. So when we are talking about a list data structure, let us assume that okay, the example that was used in the course material was actually a sentence, which is like a string of items. So I would like to use probably as well. Let me say um, sorry. Okay, there is this popular word that we use in programming. It is called hello world. But let me just use I'm very sorry for this. Okay. Pardon my big handwriting. It's not really comfortable. So I'm using a there. So these are like two separate words. We have one, we have two. So, illustrating this in a linked list, we are going to have something like these ones are even too short. Let me make this thing like a three statements. Say how are you? Okay. So yeah. Now representing this in a linked list, we are going to start from the beginning by drawing our box. And let me switch to. I'm going to have something like so this is going to be my how. Sorry, it is very, very small. Then this how will be linked to it's an arrow that is pointing to another box. So we have uh so we have an arrow that is pointing to another box. Then this will be your U. So this is what a list data structure looks like. So and like I said earlier, there are some elements of a list. Each of these words, each of these words is a data item. How is a data item, is another data item, and U is another data item. That's why they are represented in each of their list boxes. So now this this arrow that links one particular data item to the other is called a pointer. Now, the combination of this data item, the data item one with this pointer gives you a node. So this is a node, then this one is also another node. Now they said something here. The last pointer is called the terminator. So this last pointer, this is your terminator T. It is what tells your compiler, your interpreter that, oh, this program is getting towards the end of a particular list link that was implemented. And as you progress further, you are moving toward the end. Now, the first item is called the head, which is this our first out. This is our head. Our sounding section in my head. Anyway, the last item is also called the tail. This first item is the tail. The last item is called the tail. Tail with small letter T, head with capital letter H. So, and your last pointer is called the terminator. So, and the combination of a particular data item with your pointer is a node of data. So that's how you illustrate a list data structure. All right. Oh, Mr. Michael, I don't understand what you are referring to when you said it's two in the material. Anyways, I'll be moving to the next item, which is talking about a digraph. Um, okay, let me just. Okay, the question says, "We right? Uh, I don't know if everybody can see it on my mobile. I just want to quickly talk about what makes a tree a search tree, a little bit of a digression. All things being equal, a tree is something that looks like this.
Good.
Um,
What you're asking us.
okay. Well, if you can also talk to us about it, sir. What is a tree, sir?
No, you were quiet. I just thought you were asking us. I was confused.
Something happened here that I was wondering what happened, and I just lost connection on my computer, so that's what happened. So I don't know if my illustration is good enough to explain what a tree is, but basically, this is when we say a tree, you have something that looks like this. So, but the tree we are making reference to in programming is something that takes a shape like this. It has leaves, it has branches and everything that comes up like this. So you have your tree as something that looks like this. You have a root node, which happens to be the parent. So if it is a binary tree, it's going to be like it's always be subdivided into two subtrees. So, but if it is probably a KD tree or um, an AVL tree or okay, an AVL tree is still a binary tree. But if it's a KD tree or a tree that is more than two, you can probably have more than two subdivisions of the subtrees. So you have the roots, so which is like subdivided. Let's assume that this is a binary tree subdivided into two. So this one will also be subdivided into something like two. This also subdivided into something like two. So at the end of the day, you have your tree data structure looking like something like this. So that's what a tree data structure looks like in programming. So when we say what makes a tree a search tree, when you are searching for something, that means there's a particular something that you are looking for. So the whole process of going through a tree from one node to the other, probably you start from the last one. Sorry. So start from the last one, then you move up a little bit. So when you come here, you can probably say, okay, oh, let me move up a little bit again. Then you come back a little bit again. Then you come down a little bit again. Okay, this one has been missed. So then you like the whole process of tree traversing. So traversing is when you move from one point to the other, or from one node to the other on your tree. So this is what a tree looks like, in a tree data structure looks like. So what makes a search tree? What makes a tree a search tree? A tree can be called a search tree, it must support search, addition, removal of items from the side from the tree. So you have your tree, you must be traversed through the tree and look for a particular item in the tree. You must be able to add items, probably add another node here or another node here, another node here, another node here, another node here, another node. So it must be able to support um, the adding the addition of data item to the tree or removal of data item from the tree, like probably popping up a node, like probably the last one, or let me just say popping up this one, or probably popping up something like this. Then all this one must find a way to readjust and balance themselves. I think the search tree that does that balancing very well is that AVL binary tree. So it does a balancing, like it has a way of switching from the left to the right or from the right to the left when something is not balanced on the binary tree. So before a tree can be called a search tree, it must be able to search, it must be able to add, it must be able to remove something from that particular tree. So that's that about a search tree. Okay. The next question is hash table. Yes. When we say a hash table, I would like a table on its own where it has it's not able they call it a container or like an interface. But you can think of it like a table and it has a particular function for accessing the values in your what's it called in your hash table. So for an hash table, your function can it's not that is used for all. So your function is going to determine efficient your hash. Before I go deep further, before I like move from this, I would like to dwell a little this hash. the whole concept will arise from a better way to do some search and sort. I believe I've been making mention of binary since morning. So okay, let me do this.
So your screen is not showing.
Is it coming? Is I believe the screen should be up now.
Yes, it's up.
Manager.
Thank you, sir. So this is 9:18. By the grace of God, 9:30, I will be starting this class. So wherever we get to by 9:30, that will be where we'll stop. So hopefully we'll still be able to do hash table. So there's something we call linear search. So linear search is it has, when we look at the complexity of a linear search, let's assume let's assume we have a list of number. Let's say 1, 2, 3, 4, 5. Let's say you have another list of number that says something like 3. Sorry. We have 3, 1, 5, 7. Now, when you are doing a linear search, one thing about a linear search is that it is going to be moving from one data item to the other and going one after the other. So the fact that it is moving one space at a time, it has the complexity or the complexity of this algorithm, of a linear search algorithm, is said to be O of n. Is the big O notation where the O means order, the order of complexity. O of n. At how fast and how efficient and how this thing uses space management and like the time and space complexity is dependent on the total number of items it has to search. If your number of items is just 4, that means it's moving 4 times. So before you know it, it is done. It will be fast. But if it's like 1,000 items, it will have to be going from 0, 1, 2, 3, 4 before it gets to 999. That's going to take a very long time. So that means the efficiency of this algorithm is limited by the total number of items. We call it an O of n. Then that brings about the introduction of a binary search algorithm. So a binary search algorithm, it implements something that is looking like a divide and conquer algorithm. So it is divide and conquer in the sense that yeah. Another thing to also note is that for a linear search does not necessarily need to have its data in an arranged or orderly or sorted data. Take for example this first list of number. It is sorted. It is starting from 1 to 3 and it is ascending and increasing. But this second one is not sorted. It's like 3 goes down to 1, increases to 4, 5, then goes down to 7. You know that it's not a sorted number. But this first one is sorted. So for this sorted number, you can very quickly do your binary search algorithm on it. So binary search sort of uses a divide and conquer algorithm. So what it does is, if you are searching for a particular number, it will first of all divide the whole length by 2. Then it will check if that number is greater than or less than what you have in the middle. Take for example now, this is like 5 list of items, and let's assume that we are looking for 4. So it will go to the middle being 3. Okay, it will check the 4 that I'm looking for, is it greater than or less than 3? If it is greater than or equal to 3, it will come and look for it in the right hand side. So that means if it is greater than or equal to 3, it's going to if it is equal to 3, then that means 3 is it. But if it is greater than it, it will come and look for it in the right hand side. But if it is less than it, it will come and look for it in the left hand side. That is why the arrangement of items on the binary search tree is such that when you have the root node like this, let's assume that 1 is our root node, right? Sorry, 1 is our root node. Then the next one being 2. We are going to check, is 2 greater than or less than 2 or less than 1? If 2 is greater than 1, it will come to the right hand side. If it is less than 1, it will come to the left hand side. That's how a binary tree actually is sorted out. So it uses some sort of divide and conquer. So at the end of the day, when you now have the analysis of the algorithm done, it is going to be a logarithmic what's it called? A logarithmic result. You are going to have your order of complexity to be O of log n, if I'm not wrong, O of log n. So this means it will actually be faster than O of n. So irrespective of the length of the size of the data set that you are searching or you are dealing with, your what is it called? Your O of binary search will be faster. But the disadvantage of binary search is that if your data set is not ordered, then you will have no other option other than to come and rearrange it first in an ordered way. So by the time you do that rearranging, you will be having this O of log n to go back to O of n, which is the downside of your binary search. This is where your hash table now comes in. So the hash table source tends to use some sort of indexed, what's it called? Index storage system. Index storage system in the sense that, I said something about your hash table being like what's it called? Like a table. So it's supposed to be in two places, but anyways, let me just leave it like this. The main point of your hash table is to make sure that the analysis of your algorithm is O of one. Or that the time it will take to search 1 million items should be the same time it will take to search one item. So working with okay, I'll probably work with any list of data. I'll just pick this second one to work with this our data set of 3, 1, and 5, and 7. So we are going to have, let me call that first one my index I, and then we have my hash function f of x, or I'll just use it as a h of x. Then I have my h of x. So the basic idea of your hash function is one such that your where can I quickly write this one? Is one such that your h of x is equal to x. So it takes in a particular value and it returns the value, the what's it called? The exact value. So the only way this one can be very, very efficient is such that if you are putting 3, it will make 3 the index of your hash function. Then it also make 3 the value. So let me call this one. Sorry, I made a mistake here. Let me. I want to quickly redraw my table. Let me remove this one. So I have this one here. I have this one here. Let me put my h of x. Then my values. So by the time I say, okay, what is the h of 3? Judging by the fact that I'm saying h of 3 should also be equal to 3. That means my h of 3 will be 3, my value will be 3. My h of 1 will be 1, my value will be 1. My h of 7 will be 7, and my value will be 7. So, but, sorry. I made a mistake. No.